Good morning. Welcome to class. It is Monday, May 11th. We're getting right there up towards the end. Your AP test is going to be this Thursday at 3 p.m. So make sure you're kind of ready for that, right? So Thursday at 3 p.m. If for whatever reason you're not in the central time zone, make sure you look up when your actual test is. And I would suggest looking here. So yeah, a few of you have some tests coming up, mostly those of you in calculus. So good luck on your calculus exam tomorrow afternoon. Um, Everyone else, I think most of you juniors don't have anything until next week. So this week is going to be pretty busy. We're going to be going through a lot of things. Um, Now, I can't assign any more grades for this week, so don't look at this and think, oh, it's just not going to be a grade. I'll find a way to improve your grade elsewhere. So if you do these, I'm still going to be working on your grade. These are really important, just right up to the end of the week. Just work for a few more days for me, and then it's all over, and then you get your summer. All right, so just keep working, even though these aren't counting directly as a grade, they're still extremely important. Um, yeah, so we have class today. We'll do this, go through, get this turned in. Try to turn it in through the College Board website. The same thing as before. Try to figure out your setup for the AP test. Tomorrow at 2, I'm also going to have some tutorials where we're going to start working on your cheat sheet, and I'll help you through that. So everyone who isn't in calculus should be able to be there. Everyone else, again, Wednesday we will have a class, and I'll keep working on the cheat sheet, helping talk you through things, like go through every equation that's going to show up on there, things we can talk about, trying to organize things for you. And then on Thursday morning before the test, again, we'll have class at 10. I don't want to stress you out with like really difficult questions and going through AP problems. So we're going to do a little bit more of like a review mind mapping type thing. That's going to be a little bit, it's not going to be super rigorous going through a problem like we are today, but it's still going to be really good to be there. So if at all possible, try to be here, try to do this today, tomorrow afternoon if you can, and then Wednesday and Thursday in the morning at 10. Yeah, just try to be here. It's going to be really important, really good things to practice for this year's AP test. So those are the big things. The other big thing is grades are all due next Monday. So if you have any late work, be getting that in throughout the week. After Monday, next Monday, yeah, if you don't have it turned in, you're just going to have to make up credit during the summer. And I don't want to make you make up credit during the summer, so get your work in. All right, so today we're going to go through questions that have actually been put out through College Board and Advanced Placement. So these are probably the most important questions we've gone through in review so far. So again, please, please, please do these and take these seriously, because these were put out by College Board and they attempted to make these in the style that the AP test will be like this year. So these are the most relevant questions you can go through. Out of all the things to put the most effort into, this is it. So just take these seriously, really try to do these. And I don't have a key for these, so you're just gonna have to watch the video. Yeah, sorry, I don't know if they put out a key anywhere. I couldn't find it. Someone might find it. If you do find the key, feel free to post it here. It's not cheating. It's fine looking at the key for those right near the AP test. All right, so we have right here, the first thing, we have, it looks like a pendulum, but it's going in a circle. If you remember, we called this a conical pendulum. We did this a little bit earlier in the year, not earlier in the second semester. So a small sphere of mass m is suspended by a string of length L. The sphere is made to move in a horizontal circle of radius r at a constant speed as shown above. The center of the circle is labeled at point C, and the string makes an angle theta naught with the vertical. Two students are discussing the motion of the sphere and make the following statements. So I'm just going to talk about student 1 and then do A, because these are the ones that are connected. And also, if you look through these, a lot of these are independent questions that you don't necessarily have to do one right after the other, so feel free to skip around. Also, this is a 25-minute question, so time yourself for 25 minutes when you're doing this one the first time. All right, so what aspect of student 1's reasoning is incorrect, and explain? None of the forces exerted on the sphere are in the direction of point C, the center of the circular path. Therefore, I don't see how there can be a centripetal force exerted on the sphere to make it move in a circle. So what's wrong about student 1? There is a centripetal force, so there's no force directly towards the center of the circle, but what's causing the centripetal force? So tension, so it's not the entirety of tension, but we can see that tension pulls up and to the center of the circle. Circle on the mass. So that means there is a centripetal force. It's actually not going to be cosine. It's going to be sine here. We'll get into that in just a second, though. This is one of those messy ones because look where the angle is. The angle is at the vertical. It's at the top of the triangle, not at the bottom of the triangle. All right, so the tension pulls up into the center of the circle on the mass, and that means so a component of the tension causes the centripetal force. All right. So there is a centripetal force, so that's what they're wrong about. Student 2, I see another problem. The tension force exerted by the string is at an angle from the vertical. Therefore, its vertical component must be less than the weight mg of the sphere. That means the net force on the sphere has a downward vertical component, and the sphere should move downward as well as moving around in a circle. So what's wrong with student 2? So tension is at an angle. That means the tension is less than the weight. Yeah, that tension force is greater than the weight. So the overall tension force is greater than the weight. So that is what's incorrect. So B, the tension force is greater than the weight of the mass. And that's because the tension holds up the mass and makes the mass turn. So that tension is responsible for the centripetal force and the weight. Another way of putting that is that tension causes the centripetal force and balances out the weight. So yeah, they're wrong about the tension force, and they're kind of thinking of this like if you put a mass on a slope. I mean, this is how we were at the beginning of the year. When I put a mass on the slope, the normal force is less than the weight because it's not holding up the entirety of the weight as that thing slides down. But this is a little bit different because here it's staying at a vertical position, so the tension has to hold up the weight of the mass and make it turn, and so the tension force is bigger than the weight. All right, I like this next part. This next part is interesting. Some of you might have looked at this kind of confusingly. So as I go through this, think about why we're using specifically the terms in the parentheses, what those relate to. So student 3 correctly describes the equations net force is equal to the tension times the radius of the circle divided by the length of the string. And the weight of the object, mg, is equal to the tension times the square root of the length squared minus the radius of the circle squared divided by the length of the rope to relate the tension force to the net force and other quantities. So this isn't part of the question, but I really want to look at how did they get this equation? Why did they do radius divided by length here? So let's do this as a side note. So let's look at our thing thing here. So I have this linked here. I know my angle theta naught is right here. I'm just going to call that theta because I'm lazy. And then I know my radius r is here. This is the length of my string. Well, I'm trying to figure out how much of my, wait, so first of all, that net force is going to be the force along this. So I could write this as, this is my tension force. The amount right here is going to be what's causing my centripetal force. The amount here is what's going to be holding up the weight. Right? The weight is what's being held up vertically. The centripetal force is how much is this way. The tension force is this way. Another way of putting this would be like this. We have our tension force this way. We have our weight down this way. And then our tension force, part of our tension force would be up. Part of our tension force would be over. This force that's up balances out the weight. And the force that's over here is our centripetal force. So if I move this here, it looks like this, right? So this side here that's causing the centripetal force is going to be the one down here. My angle is right here, so this is my opposite side. This is my hypotenuse. This is my adjacent. So if I'm trying to find this component right here that causes my centripetal force, that's going to be opposite, so that's going to be sine theta is equal to opposite over hypotenuse. So my opposite is r, my hypotenuse is L, so radius divided by length. So I could look at this as my centripetal force, which is my net force, right? These two forces balance out, so this is my net force. My centripetal force is that net turning force. So I could say my sine of the angle is equal to, opposite as my net force divided by hypotenuse is going to be the tension. So I could say net force is going to be tension times sine of the angle, right? I can multiply this over. But we also know sine of the angle is equal to radius of the circle divided by the length, right? They use this connection here in order to put that in here. So they used a lot of trig right here saying that radius divided by length is equal to sine of the angle. So they got to the net force is equal to the tension times radius divided by length, because that's equal to sine of the angle. I thought that was really clever. I appreciated that. So that's how they got this equation. So let's see how they got the other equation. And by the way, this is how we see this is equal to sine, not cosine, because we have the opposite here because our angle is vertical. All right, and again, a thing that's real interesting is the people who created the test kept talking about centripetal force, and then they released a practice question about centripetal force. Unless they're saying, like, doing like some sort of red herring to throw us off, it really sounds like there's going to be a centripetal force equation. And I can imagine them doing some trig like this. So, all right, so we have that. Let's look at the other equation. The other equation is a little bit messier. It's the square root of L squared minus R squared over L. What is all that mess? So we have this side here. That's what they're relating. The other one is talking about weight, which is the mg is equal to this side here. So we're looking for this vertical side right here. Well, this vertical side is my adjacent side. All right, so I have the adjacent side right here. So adjacent, I have my hypotenuse, so I'm probably using cosine over here, right? So cosine of the angle is going to be adjacent divided by hypotenuse. Well, my adjacent side is going to be equal to the weight of this object, because the vertical vector here balances out the weight because it's not moving up or down at all. So this is going to be equal to my weight divided by the hypotenuse is divided by my tension. So I can multiply tension over. So my weight is going to be equal to the tension times cosine of the angle, which again, this is how we've done this most of the year. So we see up here, this is going to be tension times cosine of the angle is equal to the weight. And then we saw tension times sine of the angle is our net turning force, our centripetal force. But again, we can use another definition here, right? We can use our ratios for trig. Instead of doing cosine of the angle, they put their ratio over there. Well, cosine, again, is adjacent divided by hypotenuse. So cosine theta is adjacent divided by hypotenuse. We could look at this with our forces, or we could look at this angle with our measured values of length. So adjacent here, oh, that's not good. They didn't tell us what the adjacent side is. But we do know the hypotenuse is length L. So how would I get the length of this adjacent side? We could use cosine, but using these two lengths, I have the length of my hypotenuse, I have the length of this side. How do I get the length of that side? Pythagorean theorem, a squared plus b squared equals c squared, right? So I could do, I'm trying to find the length of my adjacent. So the side of my adjacent squared plus this other side is r, the radius of the circle squared, is all equal to c squared is the length, right? So I could subtract r squared over. So the length of the adjacent side squared is going to be length of the rope squared minus the radius of the circle squared. Or the length of my adjacent side is going to be the square root of the length squared minus the radius squared. And so I could put this in for the length of my adjacent over here. So instead of cosine theta right there, I can write this weight is equal to mg is going to be equal to the tension times, instead of cosine, I'm going to write the ratio of the sides as length squared minus radius squared divided by the length. So I can get the weight is equal to tension times cosine of the angle, or I can use cosine of the angle is the ratio of the adjacent divided by the hypotenuse. So that's not crazy trigonometry, but you definitely have to understand trigonometry like pretty well in order to be able to do that. So that's not what the question is actually going on about, but just a really good thing to think about, that they could easily ask about these equations and make you think about one of those ratios. But this is how they got those equations. So that's completely extra information, which I still think is important. But now we can go on to C. So C wants us to explain how one of those equations right there can be used to challenge student one's claim. So again, let's look at this again. So student one's claim is that none of the forces exerted on the sphere are in the direction of point C. The center of the circular path, therefore, I don't see how there can be a centripetal force exerted on the sphere to make it move in a circle. So which of these equations is causing the centripetal force? The equation on the left or the equation on the right? Yeah, that's the left equation, right? My centripetal force is the net turning force, right? So the centripetal force is the net turning force. It's kind of my way of writing it. I've never seen actually anyone write it this way, but that's kind of the best way I've come up with to describe that. So our centripetal force is the net turning force. So we see the net force is equal to the tension times the radius divided by the length. And so it's this equation right here. We see there is a net force. So net force exists and is caused by a portion of the tension, or a component of the tension is probably the better way of saying that, by a component of the tension. And that's pretty much it. That's enough. So net force exists, and it's caused by a component of the tension, and this net force causes the centripetal acceleration. That centripetal force. Centripetal. And by the way, on the test, if you get to the point and you're struggling to spell anything, just write it out. As long as it's close enough, you'll get the points. All right. And then that kind of helps seeing that this tension times sine of the angle is equal to this. So if you really knowing your trig would kind of help you relate these quantities together. All right, then we get to D. D wants us to explain how one of the equations can be used to challenge students 2's claim. Well, it's probably going to be the other one. So 2 said they saw another problem, the tension force exerted by the string. Yeah, the test always rewards partial credit. So yeah, write out whatever you can, and then any partial credit you get will be good. Normally, partial credit is only awarded for good reasoning as opposed to just writing a correct answer with bad reasoning. So yeah, any correct reasoning you should get. It's not that there's no partial credit, it's there's no partial points. So let's say C is worth 2 points. You either get 0, 1, or 2 points. So there is partial credit. You just can't get a half point, is what I was saying. Yeah. All right, so here, student 2 was saying the tension force exerted by the string is at an angle from the vertical. That means that its vertical component must be less than the weight of the sphere. And that means there's a net force in the sphere and the downward vertical component. The sphere moves downward as well as in a circle. Again, we saw that this is the part that's incorrect. The vertical component of that tension force is less than the weight. So the vertical component, well, that was the weight is equal to tension times cosine of the angle. That means we were talking about this one. So when we're talking about our vertical component, we're talking about this equation right here. So D is using this equation. The weight mg is equal to the tension times square root of the length squared minus radius squared divided by length. If you're typing this out on a computer, you don't have to type that equation. You could just say the equation on the right or the equation on the left, or hopefully they would say equation 1, equation 2. All right, so we have this equation here. There's a few ways of going about it. But let's see, L squared divided by R squared divided by L. L squared minus R squared square rooted. Is that number going to be bigger, smaller, equal to the length? For radius greater than 0, we can see that the square root of L squared minus R squared that's always going to be less than L, correct? L squared minus R squared. If R is 0, L squared minus 0 square rooted is equal to L, right? L squared minus 0 is L squared. Square root of L squared is L. Those would be equal. But if R is any value greater than 0, which again, radius can't be negative. So if the R is bigger than 0, so L squared minus some number makes that smaller than L squared. I take the square root and I get a number smaller than L squared, which means that whole fraction is less than 1, right? So the numerator is smaller than the denominator. That means the square root of L squared minus R squared divided by L is going to be less than 1. So we see that. Gonna need a second page here. And again, you would write page 2 up here and all of that. Make sure you're practicing turning these in on College Board. I want you to try to turn this one in as well on the College Board website. You really need to go there and feel comfortable logging into that, and I need to know if you can't. All right, so we see here, so I have the weight is equal to the tension times a number less than 1. So this means the tension force is greater than the weight. So we didn't have to go through all of this. It would be helpful kind of realizing, okay, we're talking, person 2 is talking about the vertical forces. Vertical forces, well, I'm either talking about net force equals tension times this value, or weight equals tension times this value. So even if you didn't see all this trig happening behind the scene, which I would guess is probably 80% of you probably didn't immediately understand that was using trig. So if you didn't understand that, you can at least get here and realize mg, that's weight, that's a vertical force. So student 2 is talking about vertical forces, so student 2 can probably be disproved with the second equation, right? Kind of reasoning. You can also think, if you didn't get C, you can think, well, they gave me 2 equations. 2 is talking about the vertical force. That means I use the second equation. That means probably C could be disproved with the first equation, right? Just kind of things that you can guess through even if you don't know. But then we get to this equation here, then we see that L squared minus R squared divided by L. So if R is any value bigger than 0, L squared minus R squared, when I take the square root, is going to be less than L. So this whole number here has to be less than 1. So I have to multiply tension by a number less than 1 to get my weight. So that means tension has to be larger than weight, right? Because if I multiply tension by a number less than 1, I get a smaller number. So tension is bigger than my weight. And that disproves person 2, because they said that tension is less than weight. And you could go a little bit further talking about how the tension is greater than the weight. That means the tension can cause the centripetal force and hold up the weight, and the net force in the vertical direction is 0. I mean, I don't think they're expecting you to go through all of those additional steps. All right, so far so good. I really think this is really similar to what the test is going to look like. If you notice, there's a whole lot of questions to answer in 25 minutes, so there's a good chance you won't be able to answer all of these. Just go through, write as much as you know, try to write as many correct statements as you can. And then if you get stuck on something and you have no idea where to go, it's probably best just to skip that and come back to it. So yeah, and then be practicing how you're going to turn this in. So if you're writing these on paper, I would suggest you log in on your phone, because it would be easier to take a picture of it. If you're logging in on your computer, I suggest trying to type up your responses. So for this one, try doing it in the way that you're going to do it when you take the AP test. If you're going to be taking pictures, write it on paper. If you're going to be uploading on the computer, write it on a Word document. All right, so students observe that the radius r increases as the speed v of the sphere increases. Together, they derive the equation radius is going to be equal to the speed times the square root of the length divided by acceleration due to gravity. This looks really similar to our pendulum equation, which is not a coincidence. And then speed is going to be 2 pi times the angular speed, and so we even see 2 pi squared of L. So there's a lot of things that make this look similar to the pendulum equation. To calculate the radius of the circle r, followed by the sphere if its speed is v. So regardless of whether the equation is correct or incorrect, does it plausibly model the student's observation about the relationship between radius and speed? Why or why not? So they said that the radius increases as speed increases. Now, we don't care if this equation works. Does that match? Does this equation show that radius gets bigger as the speed gets bigger? Yes or no? Yes, that does model correctly. So This is E. The answer is yes. And again, you don't have to write your answer until you've gone through it. The answer is yes. We see that radius is directly proportional to speed in this equation. That means that as speed goes up, speed increases, the radius increases. There's a few ways of putting this. We can just look at this: radius is equal to the speed times the square root of length divided by acceleration due to gravity. So this is saying as the speed goes up. You could also say speed is in the numerator or speed is multiplied by the square root. We see as speed goes up, radius goes up. Direct relationship. So direct is linear and no y-intercept. So directly proportional is just going to be something multiplied by something else. And you could even put in values here. You could say that imagine the speed is 1 meter per second, the radius is going to be small. If I put in 2 meters per second, 2 times the same value squared of L over G, I get a bigger radius. You could even say that as speed goes up according to the equation, radius goes up according to the equation, because speed is multiplied by the square root. Or speed is in the numerator, right? You could write that as v over 1 times this. So quite a few ways of doing that. F is an interesting one. F says the equation does not correctly model the relationship between radius and speed if speed is very fast. Explain why. And part of this has to do with this being a form of simple harmonic motion. Remember, simple harmonic motion, our equations worked for small angles. So we see as it gets faster and faster, the speed gets bigger, the angle gets bigger and bigger, and this equation is going to get worse and worse. But that's not the correct answer. Why does this not model the relationship that speed is very fast? It has to do with the radius. What's the biggest possible radius? Radius can go to 0, though. If the speed is 0, the radius will be 0. If the speed is 0, it's just going to hang straight down, and the angle would be 0. So it does have to do with the length of the string. So the maximum possible, and the reason that, let's actually think, the reason the angle can go to 0 is it's our vertical angle. So that angle can go to 0 if the mass just hangs straight down. So if it's not moving, the mass just hangs down and the angle goes to 0. So 0 speed equals 0 radius. That actually makes sense for this, because radius is how far it is sideways. So max possible radius is the length of the string. And we could see for a large speed, we can get a radius larger than the length of the string. Also, I think the AP, the Advanced Placement YouTube channel, I think they worked through this, and I think they made it so they probably have access to like their version of a key. So I would suggest looking through their answers too. They might answer it more concisely than I do and say some things that they're expecting that I didn't quite do perfectly. So just kind of a thing to think about for additional practice and looking it up. And they might do something better than I do. It definitely happens all the time. So yeah, it's just all down to the fact that the longest possible radius would be if the string is completely horizontal and swinging around this way, so swinging really fast horizontally, and the biggest possible radius is the length of the string, but this equation just goes up and up and up. Imagine I have a speed of like 5,000 meters per second, then I have a really big speed of saying I'm going to have a really big radius, but that radius can't go to like thousands of meters long, things like that. All right. Still have quite a bit left on this one. Again, they're going to load you up with a lot of different questions, it seems like, this year, where they're going to make it to where you can't finish this. Whenever they release the AP test, yeah, I can go through that. I'll probably go through that. Assuming they release it in a similar time frame they normally do, I usually go through those. All right, so now instead of moving in a horizontal circle, the sphere now moves in a vertical plane so that it is a simple pendulum, as shown above. The maximum angle theta max that the string makes from the vertical can be assumed to be small. The graph below shows data for the square of the pendulum period versus the function of string length L, and they get a linear graph. Again, we've done this, period squared divided by length. So this all is coming from the equation period of the pendulum is equal to 2 pi square root of length divided by acceleration due to gravity. So they squared everything. So they got period squared is equal to 4 pi squared, right? You have to square everything. 4 pi squared. Then you squared the square root, length divided by acceleration due to gravity. They divided length over, so they did period squared divided by length is equal to 4 pi squared divided by acceleration due to gravity. So when they graph it like this, if they get the slope is equal to the period squared divided by length, or 4 pi squared divided by acceleration due to gravity. And we can actually use this graph to solve for acceleration due to gravity. You get our slope and set that equal to 4 pi squared over g. Thing that people do in labs or something like that quite frequently. So here they want to explain how the graph would change if the mass of the sphere is increased. How would that change? And by the way, a simple pendulum. So key phrase there, they said simple pendulum. That means this follows simple harmonic motion. That means I can use my pendulum equation. So if it's a simple pendulum, simple harmonic motion, my period of the pendulum is just 2 pi squared of length divided by acceleration due to gravity. So how does mass affect anything in here? There's no mass in my equation, right? So I could say mass of the pendulum does not affect the period. The length is unchanged. That means period squared versus length is unchanged, or no effect. So it does not affect the period. So mass doesn't affect the period. Mass is nowhere in my equation for simple harmonic motion for a period, for a pendulum, and so nothing about the equation changes. So the graph is completely unchanged. Now, H, the maximum angle is decreased. Why did they say decrease? Why did they not say the angle is increased? If I increase the angle too much, this isn't going to stay simple harmonic motion, right? A really big angle is not simple harmonic motion. We need small angle, small oscillations for simple harmonic motion. So if it's already simple at a small angle and they reduce the angle even more, it stays simple. But if they say it got larger, it could turn into not simple harmonic motion where you'd have a lot more effects. So the angle is decreased, so it's still simple harmonic motion. How is the graph affected? For small angles, angle does not affect the period. of the pendulum. And again, the length is unchanged. And that means the period squared versus length graph is unchanged. Or again, also no effect. So then we take the pendulum to the moon. Will this graph change? If I take the pendulum to the moon, will the period or the length of the string change? Well, period of a pendulum is 2 pi square root of length divided by acceleration due to gravity. What did I change here? G, the acceleration due to gravity went down, right? Acceleration due to gravity on the moon is less than acceleration due to gravity on Earth. So we decreased the acceleration due to gravity. So because we decreased that acceleration due to gravity, this is in the denominator, so we have a smaller number in the denominator, which means we get a bigger period. That means the period of the pendulum increases. Another way of looking at it is the moon doesn't pull as hard. So the moon doesn't pull as hard, so the pendulum takes more time to go through the cycle. It's not getting pulled very hard. It goes kind of leisurely, really slow through everything. So we have a bigger period of the pendulum, but the length is unchanged. So we have bigger periods. So what's going to happen to my slope? Bigger or smaller slope? For each length. I should probably not say, because this versus length, I probably shouldn't say the length is unchanged because we're varying it for all of these. I really shouldn't say length is unchanged the more I think about it. So mass of the pendulum does not affect period for any length. Or any L is probably a better way of putting that. So it's not affect the period of the pendulum for any length L. So yeah, so we have a bigger period for the pendulum for each length. That means we're going to have a larger slope. Therefore, we have a steeper slope. Or we could say a more positive slope. And again, whenever they say how does the value change, it's not enough to just say it changes. Just saying period changes is not going to be enough. We really need to say period goes up or goes down. All right, keeping on going. Sorry this is taking so long. Again, there are just so many parts here. I think this is the whole point, is it makes it a lot harder to cheat if they give you a lot of parts. And so I think they're going to make it to where it's hard to finish. And don't start struggling. Don't try to take more time than needed when you get towards the end and then forget to turn in your answers or run out of time to turn in your answers. So I would expect not to be able to finish everything on this test unless you immediately understand everything, is kind of how it seems like this is going to be. All right, so here we have a graph showing the angle theta from the vertical as a function of time for the pendulum. So how far the angle goes side to side for that pendulum. Explain how this graph shows evidence for a net force acting on the sphere and how it shows this net force is a restoring force. This is kind of a tough question. Honestly, I would put this more in a calculus type question, but let's go through this. So how does this graph prove that there's a force? Well, let's put it one way. So angular speed is going to be the change in the angle divided by time, right? Just like speed is change in position over time. So my angular speed is change in angle over time, or something I could write as change in angle over change in time. Well, notice I have an angle versus time graph here, right? Angle versus time. So angle divided by time, that's looking like slope is change in y over change in x, or change in theta over change in time. So that means the slope of the theta versus time graph shows the angular velocity. All right, so we have the slope of the theta versus time graph shows angular velocity, right? All the way back to the very beginning of the year with all this stuff. Just instead of distance over time, it's angle over time. Well, angular velocity, is my slope constant or changing? Well, it's a curvy line. So I have a curvy line. That means my slope is changing. Slope of that theta versus time graph changes. That means my angular velocity changes. And that means there is an acceleration. Net force. So that means the acceleration is not 0 meters per second squared. And that means a net force exists. All right, so theta versus time, the slope of our theta versus time graph is going to be angular velocity. I see that the slope changes. That means my angular velocity changes. That means I have an acceleration. It's showing an angular acceleration, but if I have an angular acceleration, I also have an acceleration. All right, that's the easy one. Proving the net force is a restoring force. I'm trying to think of how I was going to do this. This is way easier to talk about with calculus. Yeah, actually putting this into words is going to be kind of tough. So let's look at the region from here to here, from 0 to 0.25 seconds. That's probably the best way. 0 to 0.25 seconds. The slope of the theta versus time, which is our angular velocity, gets more steep and negative. And that means we're accelerating towards equilibrium, right? The steeper the slope, the bigger the angular velocity, the faster we get as we move towards equilibrium. So we speed up towards equilibrium. Then I can look from 0.25 seconds to 0.5 seconds. This is going to be the region down here where I go and I slow down. So from here to here, I'm getting less and less steep. So less. So the angular speed, that slope, gets smaller and goes to 0. That means we slow down as we move away from equilibrium, as the mass moves away from equilibrium. And then we can keep going through all this, right? So if it's a restoring force, it always gets pulled towards the center. So here I speed up as I move towards the center. Then I slow down as I move away from equilibrium. Then I stop, horizontal line. Then I get steeper and steeper. I speed back up as I move towards equilibrium. Then I get less steep and I slow down away from equilibrium. That's one way of looking at it. The other way that we could really go through it is looking at concavity, right? Remember, going from position time to acceleration time, we're looking at concave, like how concave the shape is. Going from here to here. So here we have concave down, which means we have a negative acceleration. From here to here, we have a smile, so we're concave up. Acceleration, and then we're on this side, we're concave down again. So we have a negative acceleration. So restoring force is always pulling towards the center. So up here I have a positive angle. Here I have a negative angle. So I can see if I'm in the positive, I have a negative acceleration. So I'm pulled down towards the center. And if I'm below the x-axis, I'm pulled up towards the center. So that's another way of looking at it. If I'm in the positive area, my acceleration is negative, pulling me back to the center. If I'm in a negative angle, my acceleration is positive, pulling me back towards the center for that restoring force. J, there's so much packed into question J that it's kind of ridiculous in my opinion. We're just going to keep moving on with that one. Hopefully it made sense. If it doesn't make sense, feel free to ask me tomorrow during tutorials or at any other time. I can help you more with that. And then K is even harder here. This is kind of difficult to explain, but we'll do it. I think I have an easier way of doing this. So here's a sphere swings back and forth. It must also rotate a small amount during each swing. This is a really tricky question. So the figures below indicate the direction that the spheres rotate as it's swinging in each. Certainly is the sphere moving along, but the sphere itself has to kind of turn as it spins. So, I mean, it's kind of like you're going along this way. So relative to the string, it's not spinning. But if I look at this, it is turning as it goes along. So I can imagine if I'm looking at the stationary, it is kind of like the mass is spinning a little bit as it goes around. I'll not get too much into where else that shows up in physics, but yeah. All right, so in order for the sphere's rotation to change direction, a torque must be exerted on the sphere. So yeah, if it's not staying perfectly still, it is turning with the rope. That means there has to be a torque acting here. When the sphere is at its maximum rightward displacement, what is the direction, clockwise or counterclockwise, of the torque exerted on the sphere with respect to the point of attachment between the sphere and the ring? Sphere and the string, I mean, sorry. Briefly state why the torque is directed in the direction you stated. Now let's draw a picture here. That's probably going to be the easiest way to do this, as opposed to really trying to think about it. So I have the string here. What's the only force? What are the forces acting on the string, actually? Not the only force. Well, we have tension, right? So this is the point of attachment. My tension acts from here. What else do I have? I also have weight, and weight acts from the center of the mass pulling down. And that weight is going to be smaller than the tension. It doesn't matter as much for here. Where is my pivot? Where is this mass trying to turn about? My pivot is where the mass is attached to the string. Right? The mass can spin about that point where it's attached to the string. So I can kind of move sideways about this. So my pivot here, the tension is not causing a torque, right? it's the force of gravity that's causing the torque, because that's pulling a distance from here to here. So torque is radius times force times sine of the angle. There is actually an angle here. Tension is pulling directly to the center of the mass, so tension is not causing the torque. It's the weight causes the torque. Weight causes that torque. So getting here, which way is the weight trying to turn this? Is it trying to turn it this way, or is it trying to turn it that way? So it's trying to pull it down. So if the weight pulls it down, it's going to spin this way. So if it spins this way, is that clockwise or counterclockwise? Yeah, this is going to be clockwise. So the weight causes a clockwise torque. And then actually putting this into words is a little bit challenging. Let's say so it pivots where the string attaches to the mass. We can say the pivot is to the left of the center of mass, and that center of mass is pulled down by gravity. How would I actually like? So pivot is to the left, it gets pulled down, so it gets pulled clockwise. I mean, I would. It's hard to write. I would just draw a picture if possible. I know you can't type this up, but yeah, I would just draw the picture here, and I have the mass here. It gets pulled down, the pivot here, and because it gets pulled down, it's going to turn it this way. So yeah, so the pivot is to the left of the center of mass. That center of mass is pulled down by gravity, and that means it's pulled clockwise. And you actually get into some really weird things here, like how many days are in a year? Well, the Earth itself spins around 365 about days in a year. But if you include that the Earth went around the sun, it actually rotated 366 times. And so there's like a year, and then there's what's called a sidereal year. So another way of saying the torque must be clockwise, probably what they were going for, honestly, without all of that. Actually, that's probably a better way. So we could say as we're going here, it's turning counterclockwise, and then yeah, it's about to turn clockwise. And so when it's going to the right, it's turning counterclockwise. When it's going to the left, it's turning clockwise. I mean, actually, that's probably what they're getting at there. Not going into the detail. That's probably a way better way of explaining it. So what you would say, the mass is turning counterclockwise. When it gets to the right, it's stopped. And then when it's going to the left, it's turning clockwise. That means the torque has to be in the clockwise direction to stop the counterclockwise motion and start the clockwise motion. That's probably a better way of putting it, dealing with change in angular velocity. All right, we've been going on a really long time. Let's keep going through this. Sorry this one's taking so long. But yeah, these are just long questions. All right, let's keep going. If you do this one and get this turned in, I'll make sure your grade is improved greatly, especially if you're a person who's not passing at the moment. So if you know someone who's not passing, tell them to do this, and I'll help their grade more so than other assignments. All right, so here we are. We're on a Ferris wheel, or at least the book is. Passenger compartment on a rotating amusement park ride contains a bench. I'm pretty sure Ferris wheel isn't copyrighted anymore. I think they could just say the word Ferris, even though Ferris is a person's guy's name. contains a bench on which a book of mass B is placed as indicated in the dot on the figure above. So we have the dot right here. We have a enlarged picture of the cabin right there. The bench remains horizontal throughout the compartment's motion, so it stays in this exact same motion. It doesn't turn upside down or anything. The right figure above shows a magnetized view to the compartment. The graph below shows horizontal component of the block's position as a function of time, where plus x is the direction to the right. So we start at a position of 0 meters, and then we go sideways to the right to a maximum negative amount. Right here we're on our negative side, so we get to the maximum negative value right here. Then we keep going up, and then we get to the highest point. At the highest point, we're at a 0 horizontal position. So when we get to the highest point, we return back to 0 horizontal position. And then we go from our highest point over here. And here we're furthest to the right. So we're furthest to the right over here. So we have the maximum positive position. And then we return back to this point, which is at 0 horizontal motion. So we're back to our 0 position. So this is kind of tricky. We're looking at, we go in the negative direction, and then we reach our maximum sideways point at the side. Then we move back to the side at the highest point. We're at 0 sideways displacement. We keep moving down, and then we get to the furthest point right, and then we move back to the center. So we're only looking at our side-to-side motion. We kind of go this way, that way, and then back by the time we return to 0. All right, so A, explain briefly how the graph could be used to determine the period of revolution of the book. Well, we can just look at the graph. Honestly, kind of so simple, I don't know how to put that into words. We would say, I mean, you could go from peak to peak or trough to trough. It's kind of weird. We haven't done graphs yet, or we didn't do waves motion, which would be really helpful with that. But yeah, so we could look at this and we could say at 0 seconds. How would I write this without, because we haven't talked about graphs yet, or wavelengths or frequency or anything. 0 seconds, we're at 0 meters and moving in the negative x direction. And then we see how much time until we return to the 0 meter and are moving in that negative x direction again. And if we actually go, we see our period is something like 120 seconds. So it takes 2 minutes to go around. So we're looking here. So we pretty much just line this up to the motion and see how long it takes to go around once. So we start at 0, we go negative direction, we end up back at 0. But here we're at our lowest point, here we're at our highest point. So here we're moving to the right. We have to wait till we get back to 0 position, and we're also going to the left again. All right. B, can the tangential speed, not the angular speed, be determined from the information given? I really hate this question here because I don't know what they mean by information given. Do they mean information from the entire question or information from the graph? If the question is information only from the graph, the answer would be no. But here the answer is actually yes, calculating tangential speed. So how could I get tangential speed? Well, we're going in a circle. Speed is going to be distance over time. We go in a circle. So we could do angular speed times radius, which would work. I'm just going to use, we move in a circle, so the distance is going to be circumference over time. Circumference is 2 pi r divided by time for one revolution. So this is going to be period of the revolution. So we just have to do 2 pi times the radius, which they gave us was r at the very top up there, circular path of radius r. So 2 pi times the radius equals the circumference. And then we have period equals 120 seconds, and we can just do that circumference divided by the period. Right, same thing when we're finding the orbit. And if we do 2 pi r, it has to be divided by the period, not just any time, because 2 pi r is the amount of time to go in one complete circle. The period is the time for one complete circle. So it has to be circumference divided by the period. We could go through and get angular speed. Angular speed is going to be, it goes 2 pi radians in 120 seconds and then multiply it by the radius r. So yeah, you can do what you said, Tam. You just have to do it slightly differently. So either one of those works. As long as we're allowed to use the radius r, it's kind of unclear if they're saying we can use the radius r or not. I think they're saying you can. All right, now we're looking at the book at the lowest point on the circular path. Indicate in both words both the direction and the source of each force. What forces act on the book at the lowest point? Weight, obviously. What's the other force? Normal force. Which force is bigger? It doesn't ask that, but which one is bigger? They are not equal. Yeah, our normal force is going to be bigger. And again, that's because we're at our lowest point, so we're going down, but we're going to start going up again, right? And don't draw this dashed line if they ever ask you to draw a free body diagram, which they won't this year. But yeah, we see we're going down and we start going up. That means I'm having to be pushed up. I have to have a bigger upward force in order to start turning upward. Otherwise, if I have equal forces, I'm just going to keep going to the side. So I have to have a bigger upward force in order to change direction. This didn't ask for that. That'll show up in another one later. But so we have normal force. What's the surface? They're just called on bench. Normal force. So bench on the book upwards. And then we have the force of gravity on the book down. So normal force up, weight of the book down. And then it says direction and the source of each force. So when it says source of the force, I wouldn't write weight. I would think if you just write the word weight for this one, that doesn't indicate the source of the force, because the source is the weight caused by the by gravity of the Earth. I don't know. They probably would count weight still. You do not have to compare them, no. So comparing them will be useful later on. So you don't need to actually compare them until we get to part G. So this is completely unnecessary. You do not need this in your part to get answered. All you need is normal force up, weight down. As far as I can tell, I don't have the key to this. But yeah. All right. Now we have 3 students. One of them is right. 2 of them are wrong. So at the lowest point of the circular path, the book is moving only in the horizontal direction, right? Because it was moving down, but it has to stop moving down before it can start moving up again. For that brief instant in time, the book is not moving up or down, it's only moving sideways. So they're discussing the force of friction on the book. Here are their arguments. So student 1, at the instant the box is at its lowest position, the book experiences no force of friction at all because the net force is only in the vertical direction. Student 2, at the instant the book is at its lowest position, the book experiences a force of kinetic friction because the book and the bench are moving to the right. And student 2 is so wrong that D is asking us how to say they're wrong. And student 3, at the instant the box is at its lowest position, the book experiences a force of static friction because the book doesn't slip relative to the bench. So D wants to know why student 2 is wrong. So why is student 2 wrong? It has to do with kinetic friction. So they're saying the book experiences a force of kinetic friction. The book and bench are moving to the right, so it must be kinetic friction, right? But what has to happen for kinetic friction? It's not that something is moving, right? When this is rolling without slipping, it's still static friction. So we don't care about motion. So kinetic isn't about just the object moves, but the object does what? This would have to slip, right? That's kinetic friction if they're slipping between the two objects. So this would be like a car tire on ice. But if you're driving and your car is under control, like on a normal road, the tire doesn't slip at all, that's still static friction. So kinetic doesn't just mean motion. Kinetic means motion between the two objects, sliding or slipping. So for kinetic friction, one object slides or slips across another surface. Another object / surface. Because it could be a large surface. So it's not just that they're moving. If they're both moving and they're not slipping, that's still static friction. They have to slip. So they have to slide. So here, the book does not slide. That means there is no kinetic friction. Which is why, again, I don't like every single time whenever we're saying less than or equal to for the magnitude of force of friction is less than or equal to the coefficient of friction times the magnitude of the normal force. The question I always ask is not, are the objects moving, but is there any slipping or is there sliding? Is there any motion where the surfaces slide one across the other? And I actually stabbed myself with a pencil. All right, so no kinetic friction because they're not slipping or sliding. The book just stays at rest. So who's correct? Student 1 or 2? Is student 1 correct that there's no friction at all? Or is student 3 correct that there's static friction? So take your votes, 1 or 3. 50% chance. Oh, hey, Dan, I didn't even notice you got here. This is a really tricky question. Yeah, 3 is the one they're trying to get you to answer. So they intentionally wrote 3 to try to get you to answer 3. It is actually student 1. But yeah, 3 is the one they're expecting you to choose. So yeah, no force to counteract friction at the moment. So yeah, let's kind of look back to here. So we're moving to the side, but it's not moving, right? We don't draw motion on a free body diagram. What do we draw on a free body diagram? Force. Now, we have a constant speed to the left, right? So we have constant speed. Yeah, we could write it that way. We don't have a constant velocity. We have a constant speed, not velocity. right? Our velocity changes because we're going in a circle. We're changing direction. But we have a constant speed, right? Because we have a constant speed, we have normal force and weight are vertical. We have no sideways forces. Right? Because we're a constant speed, if I had a sideways force, we would speed up or slow down, right? No sideways forces. If I had a sideways force, my speed would not stay the same. I would be speeding up through here. So, better way of saying that would be no sideways. Yeah, it's just no sideways force. We'll put it that way. Because otherwise, the Ferris wheel would speed up. So yeah, there's no sideways forces, so there's nothing to stop, right? So when this mass is just sitting here, is there a force of friction? There's actually not a force of friction. If I start pushing it, it's going to push back with friction. But when it just sits here, there's no friction. This is going back to the whole that force of friction is less than or equal to the coefficient of friction times the magnitude of normal force. That frictional force is only going to push back however much it needs to. When this thing just sits here, there's no friction. It's only when I start moving the object that there's friction, when I start accelerating, not just moving, but accelerating. But while it's just sitting here doing nothing, there's no force of friction. It doesn't have to resist friction. Friction only resists when it has to. So there is no force of friction until I try to accelerate this thing. So we see here, there's no sideways forces, otherwise the book would speed up. There's nothing pushing it sideways this way, so there's no friction. So no force of friction needed to counteract a sideways force. And that means student 1 is correct. Is that making sense or no? I feel like I'm not explaining this very well. When we're at 90 degrees, there is no friction. This stays vertical the whole time, right? So there is still going to be no friction here when it's going up. There is going to be friction between never mind, you're right, there is at 90. Yeah, the two times there's not going to be friction are 0 and 180. Yeah, you're correct. So yeah, so it's only going to be when we're at the highest and lowest point that there's no friction. Any other time in the motion, yeah, let's say you're right here, so we will have a force towards the center. We will have to have a frictional force. So when we're at our 90-degree angle from here, so let's say we 0 degrees at the bottom, 90 degrees is here, 180, 270. So we would have to have a force of friction turning us, and then we get to this point and we would have normal force is still going to be bigger than the weight. When we get to the highest point, then we have a bigger weight than normal force. So this is 180 degrees or at the top of the motion. Then we have a bigger weight than normal force because we're going up, but we start going down. So here we go back to no friction. But then when we get to 270 degrees, when we're on the far side over here, we're going to have a bigger weight than normal force because we're going down. But yeah, we are turning, so yeah, we will have to have a force of friction. So most of the time, we're going to have a force of friction. Yeah. And it's messier throughout. This force of friction is actually changing throughout. But yeah, it's just anytime we need a sideways force, we're going to have a force of friction. But anytime we don't need a sideways force, our forces are all vertical. All right, let's keep going. We spent a lot of time on here. I don't want this to be too long. Hopefully it doesn't end up like over an hour and a half. So F, at the lowest point in the circular path, the book is moving only in the horizontal direction. And what direction, if any, is the net vertical force on the book? And then explain without deriving equations. So at the lowest point, which way is our net force? Yeah, up. So the net force is up. And we could say the book was moving down and left. Then it will move up and left. Therefore, the net force is up. So something about the net force being up, because we have to stop the downward motion and then start the upward motion. So we have to have a bigger upward force than a downward force. All right, G. Now a student is asked to derive an equation for the vertical force Fb that the bench exerts on the book at the lowest point of the circular path in terms of the book's mass Nb, tangential speed Vb, radius r of the path, and physical constants. Here is the student's incorrect derivation. Now, they did calculate centripetal force correctly. This is centripetal force, mass times speed squared divided by radius. But why is the derivation incorrect? What force are they not accounting for? Yeah, they didn't account for the force of gravity and the normal force, right? So all they have is the centripetal force, or what they're trying to derive. It just has the vertical force of the bench exerts on the book. Yeah, so they're trying to find the normal force. Yeah, they're trying to find the normal force is what they're. So they're trying to find the normal force because the force the bench exerts upward. So is it because the normal force doesn't point to the center of the? I mean, it's not completely that. It's that. What do you mean the normal force doesn't point to the center of the wheel? I don't understand your question, Pam. So we're trying to find the normal force. We have the centripetal force, but we also need to account for weight. For weight, so the centripetal force is caused by the normal force and the weight. I don't know what else I really need to put to describe that without actually writing it. Because net force, no, the net force is not the centripetal force. The net force will be the centripetal force at the sides. Actually, no, that wouldn't even be the net force. So the net turning force is going to be a centripetal force. So we have to be a little bit careful here because even at the sides, here our net force is not our centripetal force. The net turning force would be our force of friction, but these two forces are also not balanced. Actually, no, those would be balanced. What am I saying? Yeah, it is going to be the net force. I drew this wrong. The normal force and weight need to be balanced. Otherwise, this thing is speeding up in the sideways direction. Sorry about that. I was incorrect about those. Yeah, so the normal force and weight. So yeah, the net force would be the force of friction at the side points. But at the anywhere beside those points, the normal force and weight will not be balanced. So the net force is not only the centripetal force. Or the centripetal force is the net force, but the net force is not only caused by the normal force. So we could also say so the centripetal force is the vector sum of the normal force and the weight, and they did not account for the weight in this. And they said, did they say? Oh no, they didn't say without deriving anything. All right, so let's derive it. So we see that we have our forces here. We have a bigger normal force than we have weight because we're moving down and we have to begin moving up. So I have to have a bigger upward force. So my centripetal force is my net turning force. So I see my centripetal force is going to be my big force minus my small force. And so we're going to see we can add our weight over. So our normal force is going to equal our centripetal force plus the weight of the book. So they had the mv squared over r, which was correct for the centripetal force, but they did not account for the weight. So at the lowest point of the circular path is the force the bench exerts on the book greater than, less than, or equal to the weight of the book. So this normal force, is it bigger or smaller than the weight? Bigger. So our normal force is going to be larger than the weight. So the normal force of the book is going to be greater than the weight. There's a few ways of looking at it. We could just get normal force is equal to centripetal force plus weight like we got here. So I could just use this equation. So centripetal force plus the weight. So the normal force is going to be the weight plus an additional force. So obviously it's bigger. One other way of putting it, we could put this into words. We could say the bench holds up the weight of the book and accelerates the book upward. So it's moving down, it begins moving up. So obviously the bench has to hold up the weight of the book and push it up with an additional force to push it upward. And that means the bench pushes up with a force greater than the weight of the book. All right, and then finally, last question. Consider the position of the compartment at the top of the path and the bottom of the path. At which of these positions, if either, is the total mechanical energy of the book greater? And notice you can answer I without answering anything else. You could have just skipped straight to I and answered this question just fine. So in your justification, explain the source of the work done on the book which changes its mechanical energy, or explain why the book's mechanical energy did not change. All right. So mechanical energy, is it the same or is one of those bigger? Well, what's the same throughout this? Is the speed changing or is the speed constant? So we have a constant speed, which means we have a constant kinetic energy. Constant kinetic energy. There is rotational, actually. Yeah, I should probably write. Plus 1/2 moment of inertia times angular speed squared. So, but we also have a constant, so we have a constant translational and rotational kinetic energy. Our angular speed isn't changing. The moment of inertia of the book is not changing. So constant speed means constant angular speed as well. So we overall have a constant kinetic energy when we account for everything. So constant speed and angular speed, so constant rotational and translational kinetic energy. But our potential energy changes, right, though? Gravitational potential energy changes. So because our height changes. And we have the most gravitational potential energy at the top of the ride. And that means we have the most mechanical energy at the top of the ride. All right, so there's a few ways of answering this. There's a way where I think they're expecting you to answer it, and a way where it kind of also would answer it. So if the energy is not constant, then yeah, there's work done, right? So if the energy is not staying the same for the book, work is done somewhere else. So what work is being done? Well, to keep this from going too long, one thing I could look at is as this one goes up, I'm adding potential energy here, right? Let's imagine I have a person over here. Does it say? Did I not read? Is the book moving? Total mechanical energy of the book. That is a good question. Yeah, I'll get back to that, Tan. I didn't look at that closely enough, but I'll come back to that. So let's say we're looking at total mechanical energy. So what we're answering here is for the book Earth system. So yeah, we're including the Earth in this as a whole. So yeah, that's one thing. If we are looking at the book and the Earth potential and kinetic energy, one way is I would say that there's going to be a motor on here or some sort of engine that turns this and lifts the person up doing work or lifts the book up. I could also look at as the book goes up, there's probably a person over here whose mass goes down. And so I could say we're losing potential energy of the person here, which is putting it into potential energy here. That's one way of looking at it, but it's probably coming from a motor. So therefore, energy is added using an external force, which would be a motor. Yeah, that's so. Tan made a really good point. They're saying, is the mechanical energy of the book greater? I don't know. I don't know what they were intending to say with this. Now that you say that, they were really vague what they meant by the system. So if we're looking at the system that includes the book and the Earth, then yes, our kinetic energy is constant, but our potential energy changes. Here they just said total mechanical energy of the book. So that's really vague. If they were saying just of the book itself, without looking at the Earth, then yes, mechanical energy would be constant because kinetic energy of the book is constant. Um, that's a badly worded question. So yeah, the energy of just the book itself, right? If we're looking at a system that's only the book, we can't look at gravitational potential energy. We would just be looking at kinetic energy of the book. And so if the system is just the book, mechanical energy is constant. But if we're looking, the thing that makes me think of the book and potential energy is that they did call it total mechanical energy. A lot of times you don't call it total. I don't know. Yeah, I genuinely don't know which one they're asking for. So, yeah, and I don't have a key. I would hope they word this a lot better than this. So, yeah, my answer is for if we're looking at a system including the book and the Earth. Is that the key? Did they actually go through it? It's the actual. Yeah, I mean, I listed this. I didn't actually watch them go through all of it. So were they including this as a system, including? Uh, yeah, the just the ball would be rotational and translational kinetic energy. So yes, if we're looking at just the energy of the book itself and only the book and nothing external to the book, then I would say the total mechanical energy is the kinetic energy, rotational and translational kinetic energy of the book. So yes, if we are looking at just the book itself, mechanical energy of the book is unchanged because the book has a constant rotational and translational kinetic energy. So yes, if that's what they're going for here, then we would have to say, so this would be the book Earth system. I guess that's what they're going for. I wish they would use better wording than that. But this is if it's just the book system, then the total mechanical energy would just be translational and rotational kinetic energy. We have a constant speed, which means we have constant kinetic energy, and we have a constant mechanical energy. So yeah, I think he's the one who actually wrote this question. So if that's what he was going for, then obviously that's how it would be graded. Again, hopefully they're more specific than that. But yeah, I am leaning more and more now towards they're looking at just the second one. That is just looking at the book. And this is I actually really hate when the AP test does this with like really, really subtle and vague wording. Like they can ask a difficult question without making the question difficult with vague wording. Uh, but yeah, hopefully they're better with the wording on this one than this question. So yeah, if you watch the video, I didn't see whichever he goes with. You could go with that one. I guess yeah, it is looking like they were intending just the book because they said mechanical energy of the book. So yeah, I think they're going for they're the same mechanical energy. But yeah, this would be mechanical energy of the book Earth system for the one I was answering initially. All right. Any last minute questions? I don't think they released a physical key, but yeah, you can watch that video to go through it. Again, sorry this one was so long. If you do this and turn it in, I'll give you bonus points on several places. Please go through and actually attempt this. Even if you don't
write out everything. This is really important to go through. These are practice questions that are similar to what it's going to look like on this year's test. Again, it seems like they're going to ask a whole lot of questions where you don't have time to finish. You need to go to and actually go practice the submission process. Otherwise, you're going to struggle with that. And
just keep working. We'll be here tomorrow afternoon at 2 p.m. And I'll also have class Wednesday and Thursday at 10 a.m. So keep working. Have a good day. Sorry this one was so long.